So let's add some details to the surface temperature and salinity variabilities and how they are related to the surface fluxes. Okay, so here is the mean sea surface temperature, annual mean, long-term average, going from pole to pole. And you see the major features here in the tropics in terms of the ITCZ and the upwelling region. Remember, we had the Ekman divergence because of Coriolis acting on the trade winds, forcing the ocean to move westward and diverging away from the equator, piling up and warming the water along the way and creating a warm pool. Indian Ocean has different dynamics, but the Atlantic is very similar to the Pacific, except for small differences because the basin is quite a bit smaller, right? What do we do with it? We look at the net surface heat flux, which is the sum of incoming shortwave radiation, outgoing long wave radiation, sensible heat loss, and latent heat loss, right? Those are the four major components. There is penetration of the shortwave radiation below the surface, which can affect the heat budget of the mixed layer. What do we mean by heat budget? Basically, if you look at any particular point in the mixed layer, if you want to look at how the sea surface temperature is determined, then you have to look at entrainment that we talked about, advection in or advection out of the heat, and surface heat fluxes as well, right? So here is the net heat flux going into the ocean, and there are places where the ocean is losing the heat and the atmosphere is picking it up. Okay, what's happening? So dynamically, upwelling and the entrainment mixed layer processes are creating cold temperatures here, and the atmosphere is trying to damp the cold temperatures by dumping significant amounts of heat there. That's some of the largest numbers you see here, although this is on average, up to about 200 watts per meter squared. Here it's warm, but the net heat flux is still downward but small. Indian Ocean gains about 20 watts per meter squared per year to the north of about 20 south because of the various reasons in which the Pacific convection here affects subsidence over here, and so on and so forth, right? So there is, in some sense, at low frequencies on a longer time average, ocean is gaining heat here and it's losing it here. This is argued to be an important mechanism in which long time scale variabilities can happen. We will see that the ocean, to take up heat here, the thermocline has to be lifted by the upwelling, cold waters have to be brought up, and that heat is being lost here on some time scale. If you somehow reduced this heat loss, then does it adjust here by changing the thermocline and the sea surface temperatures? Or if you changed something here, does the ocean atmosphere system adjust by changing the fluxes here? There is some evidence that in fact that does happen, but of course there are other players in the game as well who have their own mind, like the sea ice here or the glaciers here, glacier on Greenland, which is here, and so on and so forth. So ice albedo feedbacks, as we will see later on, also can be important. The equivalent for sea surface salinity is remarkably different. Sea surface salinity is created also by surface fluxes. Evaporation increases sea surface salinity, whereas precipitation will decrease the sea surface salinity. So you can see the ITCZ and the warm pool clearly here with lower salinities than the subtropical gyres. The upwelling affects the salinity here in the deep equatorial region. We already talked about how the Atlantic is much more evaporative than the Pacific, and how the North Atlantic is very different than the North Pacific. And here is the net surface heat flux, which is basically evaporation minus precipitation. In the places where rivers come out, rivers matter as well. The Congo Zaire River comes out here. You can see this blob of freshwater, Amazon, Orinoco here, Krishna, Mahanadi, Ganga, Brahmaputra, Irrawaddy, and so on come out here in the Bay of Bengal. But you can see that the stark contrast exists between the Arabian Sea and the Bay of Bengal. Bay of Bengal gets as much rain as freshwater input from the rivers, whereas Arabian Sea is mainly a evaporative basin. Okay, looking at the seasonal cycle says something else as well. This is the variability of sea surface temperature from 95 to 2000, which includes a strong El Nino, which kind of creates this warm pattern all across. But in general, you have upwelling with its seasonality, strongest upwelling happening in boreal summer months. There is the whirlpool moving back and forth with the sun. So as the sun goes north, the entire whirlpool goes north. As sun goes south, the whirlpool goes south. Similar things happen here with slight difference. Indian Ocean is different. Monsoonal circulation affects the contrasts. You get strong upwelling along Somalia in the boreal summer months when the southwesterly winds create offshore transport of water and create coastal upwelling and so on. Of course, there are latitudinal seasonal variations as well, but you can see there is hardly any variation at polar latitudes beyond the polar circle. If you look at salinity, salinity doesn't do this kind of wobbling north-south, but it expands and contracts to some extent just like the subtropical highs do. So the Hadley cell and the ITCZ movement create evaporation or freshwater cycle in the subtropical gyres, and upwelling of course affects salinity. Those create seasonal variabilities, but it's nothing as dramatic, except you see again the dramatic difference between the Arabian Sea and the Bay of Bengal. There is lots of rain here. This warm sea surface temperatures always mean rain in the deep tropics when the temperatures cross a threshold of about 28 degrees, except if air is coming down. Okay, so if there is a lot of warm water here and convection happens and rising motion happens, you can get subsidence over here and create warm temperatures, and that will not convect. Okay, there are almost 5 meters of rain here on an annual average. E minus P is smaller, as we saw in the previous animation. Nonetheless, these are the main points about sea surface temperature and sea surface salinity. Dynamics, ocean advection, entrainment, mixed layer physics obviously affect sea surface temperature and salinity, and we haven't said exactly what we mean by surface temperature and surface salinity. Typically we mean averaged over the mixed layer. Remember, we said mixed layer is vertically homogeneous because of the turbulent kinetic energy creating this mixing, and those are typically referred to more specifically as bulk temperature and bulk salinity, because you can also measure skin temperature and skin salinity in some cases with satellites and so on. So in many places the balance can be just with the local net heat flux and temperatures, or local freshwater flux and salinity, where system is almost one-dimensional. But in most cases ocean's currents remove heat or add heat, entrainment adds heat, adds cooling, and so on and so forth. So the mixed layer heat budget becomes very important. I hope you appreciate the contrast that the ocean is forced from the top, so we have to worry a lot about frictional boundary layer in the ocean as opposed to the atmosphere, where we didn't talk about it at all in this book. So that is a brief introduction to temperature, salinity, and surface fluxes. Let's look at a little bit more about the mixed layer physics then in the next podcast.